started it. Actually, wait. There are a lot of new ones for you guys.
Oh, that's good. That's good. That's good. Oh, they all got lost.
So let's do it. Right back here.
We're starting, everybody. Sorry, my voice is really sharp. Okay, welcome to our second ever Micromouse lecture on motors and encoders. Please scan the QR code if you haven't already. And we'll begin. That was for a bit. Okay. Alright, so here's an overview of everything we're going to be going over in today's lecture. So we'll be covering all the two different motor types that are pretty popular and the motor that we'll be using. And then we'll also cover how we control our motor on the mouse, and that includes spin direction, so like clockwise, counterclockwise, how we get it to spin a certain direction, as well as the power that we're feeding into the motor, and how we turn on and off our motors. And lastly, we'll be covering encoders. So that's measuring basically motor rotation to keep track of where you are in the motors.
Alright, so actually before we look at the different types of motors, I want to announce that you guys stay and you guys need to read the announcements so that we get like 50,000 messages about things which we already said in the announcements. So read them. You have to like read them line for line, not like read only the things which are linked or something like that. You should actually read them all. Yeah, and also if you just got here, you can sign in. Yeah, so read them all. That way I get less questions. I mean, questions are fine, but when I get like a million of things I already said, it's not fun. That's annoying. Also, I had a beer last time and now I won't, so I am the same person. Alright, so now we're gonna look at different types of motors, which are like these are two popular types of motors, and we're gonna like walk through how we decided to use a specific one on our rat. Okay. So if you ever wonder what motors are, it's basically like a conversion from electrical energy to rotational energy. They're akin to like generators, which actually will be important later, which generators typically turn something like rotational energy or rotational motion into electrical energy. So they're very similar to generators. The type of like electrical input we use is generally of two types, which is direct current or alternating current, and it's pretty much what it sounds like. Direct current is a direct, I mean not necessarily super steady, but a direct steady input, whereas alternating current alternates like sinusoidally, so like, oh, actually you can see a little bit, it alternates like that. And then the two types of motors we're going to be looking at are brushed and brushless motors. We're going to go through that.
So the first type of motor type that we're going to go over is brushless motors. And the form of power that brushless motors take on is AC power, or AC current, or alternating current, like Michael said. So AC current is mainly used for transmitting electricity along like long distances. So a common source of AC current that you might see is like your power outlets at your house. And the pros of using a brushless motors is that it's more precise and it's more efficient. And the drawbacks or cons is that it's more expensive and it's harder to work with, largely because it requires additional conversions. what I mean by this is brushless motors, they need AC current, right? But all batteries supply DC current. So to use brushless motors, you have to convert from DC current to AC current. And then here are some common applications where you might see brushless motors. So that includes electric cars and anything that uses RC motors. And then this diagram shows how a brushless motor works. So you have an inner central magnet surrounded by several electromagnets. And by turning on and off the surrounding electromagnets, you're basically able to rotate the inner magnet. So let's give an example, right? So, okay, as soon as this is on, like this is attracting and this is repelling. So it moves it. And then again, like it's attracting and south-south repel, and then it continues to rotate. But that's how brushless motors work.
All right, and brush motors are the ones that we're gonna look at. They use DC current or direct current. They can give an example, which is like batteries, which is why it's relevant to us. They can only provide a constant current. Brush motors are generally cheaper and simpler to use, but they're like less precise than the complicated brushless motors, and they're less efficient as well. If you see this is a better diagram. It's kind of like the opposite of a brushless motor. So in the brushless motor, the permanent magnet was on the inside and it was rotating, whereas the electromagnets were stationary on the outside. In a brushed motor, the permanent magnets, which are what you see here, are whatever, stationary on the outside, and the electromagnet, which comes from this, like, I don't know what you call this, coil, rotates, and that's what generates like the rotation.
Yeah, but like you guys don't exactly need to know how like brushless motors or brushed motors work. It's just kind of good to know. But like the inner electromagnet or current carrying conductor, like there's current going through it and there's a magnet around it, right? So that creates a magnetic field. And if you use if you ever take physics, you'll learn about F equals ILX B. But then here, and then like current's going through here, and then there's a magnetic field here, so force goes up, and then it causes it to rotate and stuff. But yes. So here are just examples of the motor types that we discussed. So on your left, you have your brushed motors, and on your right, you have your brushless motors.
Oh, you spoiled it. I was supposed to ask like what we're going to eat, what we're going to use. Okay, well, it's spoiled, and so the type of motor we're using is brushed motors. Even though they're like less precise and stuff, I mean, there's multiple considerations. First of all, they're cheaper, and we don't have like $1 bajillion, and so we're gonna buy cheaper motors for a lot of people. But also, like, it's not like we super need brushless motors. Like, because of the size of our Micromouse, we don't need like lots of precision or anything like that. So the cheaper option just happens to be like very good, and like we don't really need all that extra precision. Also, we would have to convert from DC to AC if we used brushless motors, and that would add more complexity to the project, which we don't want. So our motor is brushed. It has a 30-to-1 gear ratio. Basically, that means I have to like think about it, because you can't see it on the motor here, but basically for every, imagine like there's an input gear or something like here, or like input shaft, which is what is actually like rotating from the processes we showed you earlier. For every 30 times that rotates, this large shaft, which our wheels are going to be connected to, rotates only a single time. And it has to do with the gears inside, and you can have different gear ratios and stuff, and it will affect like torque and all that kind of stuff. The ideal operating voltage is 6 volts for these motors. Then the maximum current draw is 0.67 amps, and those will be relevant later, so you can remember them. Is you?
Next up, we're going to be talking about motor control. So that's how you turn your motors on or off, and this also includes how you specify a motor's direction. That's how you specify a motor's direction, like if a motor's spinning like clockwise or counterclockwise. and as well as controlling the motor speed.
Okay.
So, like I mentioned before, these are the components that you're going to need from for controlling the motors. And that's first off the motor on and off state, so how do we turn the motors on or off? The motor direction, so specifying it clockwise or counterclockwise. And lastly, motor speed, so.
Alright, let's go into motor power, so like how we're gonna turn them on and off. So I guess the exercise we did last year, is I asked you guys like what is wrong with this tiny schematic. I can tell you that the pin is a pin coming from our microcontroller, and it's just supplying or has some voltage, and then ground is just some ground plane on our Micromouse.
And this pin is providing 3.3 volts.
Oh, the spoiler, but alright. Yeah, the pin does provide 3.3 volts. I might not have the spoiler actually. And so when this pin is on, the current will flow from a positive voltage to a negative voltage, or from high to low, and so the current will go through this motor. And so, does anyone know why this will not work?
Do you need like a driver to like change the voltage of the motor?
That's a good idea.
Well, like, I mean, why would we need that? Why would this work?
I don't think it would supply the right voltage to the motor.
Yeah, that is why this doesn't work. Because the ideal motor, so yeah. But I mean, jumping to a driver is a quick jump. You could do it without a driver, technically, or like make your own. So the ideal motor specs we talked about were 6 volts and 0.67 amps, and our pin can only supply 3.3 volts or 100 milliamps, which would not be enough to, I don't know, move or use the motor in its correct capacity. It might just not turn or turn extremely slowly or something like that. Does anyone know a solution to this problem?
Possibly an op amp.
I mean, that is a solution. We could do something like that, but we won't do that because it would add more complexity that we don't need. But we're just going to use the battery voltage instead. So if you, okay. Yeah. So we're going to use the battery voltage directly because they provide a lot more current and such, and so we can use it, and it's easier. So, oh wait, this is your
Wait, so how do we properly power the motors using our battery? So we want to obviously use our battery now because as it provides more voltage, provides that accurate voltage to power our motors. So how do we do this? We use an electronic component called a transistor. So a transistor essentially acts like a switch for your circuit. So there's actually 3 components to a transistor. So you have your emitter, you have your base, and you have your collector. And what a transistor allows you to do, it's essentially like a switch. So it allows current to flow from this emitter to the collector depending on if you apply voltage to your base. So how can we use this when powering our motors? Well, in our case, what should be attached to what? So we have the base, that is gonna be our pin out connected to our microcontroller pin out. And then our emitter and collector will be our battery, motor, and our ground. So depending on if we apply a voltage to our pin out, it'll connect all 3 of these components and allow current to flow from the battery to the motor to the ground. Do you guys have any questions, or if I went too fast? You guys all good? Okay, but yeah, so it just acts like a switch, and then it'll connect all 3 of these components when I want it to. And otherwise, if I don't supply voltage to this, to our base, which is our microcontroller pin, it won't connect anything, just like a switch.
This is me?
Yes, yeah.
Well, I mean, this is like what he said. We can basically control whether the motor is on or off using that transistor. So when we apply voltage with our pin, it allows the battery or the current to flow through the motor to ground, and so the motor will turn on. And then we just stop applying voltage with our pin to turn off the motor.
So here's a nearly completed circuit of what our how we would power our motor. So in this circuit, we have our battery at the very top, and then it's connected to our motor, and then it's connected to our transistor with a base, which is our microcontroller pin out, and then it's connected to ground. So when we do supply voltage to our pin, current, it makes a complete circuit, since current's gonna be able to flow from the battery to the motor to the ground. So current will flow and everything will work fine. But if we were to disconnect this, if we were to not supply current to this pin, this part would not be connected, and there would be no ground, so there's no potential for current to travel. So your motor would not function. So, but this is nearly complete. There's still one problem, and that problem is, okay, what is the problem? Any guesses? Yeah.
You can't control the speed of the motor?
Wait, we're gonna address that later.
That exists, that's a problem that exists, but they won't stop the circuit from working. That is also a problem which exists, but doesn't. When we asked them what's the problem with the circuit, like this circuit as of now will not work.
Yeah, like this circuit, it's like faulty. Okay, here I'll just get into it. But those are great. We're gonna address those later.
Yeah.
So the actual problem is inductance. So what actually happens is when we actually turn off our motors, right? There's gonna be no more current flowing through everything, right? So there's gonna be a decrease in current from the battery to the motor, and this decrease in current causes a decrease in magnetic field. If you don't know what I'm talking about, like you'll learn it in physics, don't worry. It's just something kind of cool to know. But so there's a decrease in current, causes a decrease in magnetic field, and then it causes a decrease in magnetic flux. And then a lot of decreases, but magnetic flux is basically how much magnetic field is traveling through a given area. So if I decrease magnetic field, of course magnetic flux is gonna decrease. And according to Faraday's law of electromagnetic induction, when you have a change in magnetic flux, this creates an induced voltage, or EMF, or electromotive force. But okay, basically, when there's gonna be a decrease in current, you're gonna get a voltage spike, like right here, right? And this voltage spike will be in the direction that opposes magnetic flux to support the current, right? So it wants to basically, because current's getting shut off, so naturally it wants to help generate more current to help it. The thing is, normally current would flow all the way to ground, right? But it can't because this path is shut off. So the only other path current can take is back up to the battery, or back up to the motor, through the battery and through other components. But this can potentially damage other components, so we don't want that. So what can we do? Okay, like I said, it generates a back EMF, or just creates an induced voltage at that, and then this induced voltage creates an induced current, which can't travel to ground anymore, so it has to go all the way back up. And then, so our new problem is, how do we stop current from flowing the wrong way? Which Michael will talk to you about.
Yeah. You don't have an answer? That's an amazing answer.
That's spot on.
Because that is, wait, is it another yeah, so we're going to use a flyback diode. If you don't know what a diode is, it allows current to flow in only one direction. And so like, it's going to help us control the flow of current through our diagram. And so normally, actually, yeah, so this is like, let me go back here real quick. So normally what happens is like, when you turn off the motor, there's a huge negative spike in voltage generated by the motor so that it can try to maintain the current. But as a result of that, earlier I said that current flows from high voltage to low voltage. So basically, current is going to try to flow up to the motor, but that voltage spike is going to be so incredibly strong that what's going to happen is it's going to cause like electrons and stuff to try to like jump through the air in our open switch. So like not exactly, like it's not even a complete circuit at this point, but the voltage is so strong, it's going to try to cause it to jump that gap, which can like basically like fry your components and stuff like that. And so to prevent that, we can use what's called a flyback diode. And so essentially what this is going to allow, and I don't know if you saw, I was like asking Spark about this yesterday, but basically it allows the motor will still have a negative spike, but it's going to be a lot smaller because what the current can do is instead of trying to get current or draw current from over here, it will go through the diode, and then some will go back up through to the battery, and some will come back, keep going through and through like that, because the motor is trying to resist change in current, and so by allowing current to continuously flow through here, it will help reduce that voltage spike.
Also, like, wait, this diagram isn't exactly correct. So, like, when current is getting traveled, it doesn't travel directly to the battery. It has to go through like the microcontroller and other components. And when there's unwanted current going through these components, it could potentially damage it. Which is why we wanted to just like make the current just immediately go back to the battery.
But that's the thing. I don't think it immediately goes back to the battery. I don't think it does.
Okay, we'll let you know. But yes.
So does the current just keep flowing through the diode until the diode like?
I think it's a combination of both. Like when I was, because the old diagram was a little bit different than this, but it just didn't seem right. And I feel like, I don't know. Let me just draw it real quick. Like if this is the motor, then this is this. You know, I'm not gonna draw the rest there. Then this. I think what's happening is the current is gonna flow like this up here, and then it's gonna flow down partially this way and then partially this way up towards the battery. Because it wouldn't make sense. Where would the thing is trying to maintain the current, right? And so where would it be getting it from? Is there just like there's zero current through here or anything?
Yeah, I think so.
How could that be? That makes no sense.
There's no current in this actually, no.
No, there is current. Because the current dies out.
Yeah, sure. I mean, maybe.
Alright, anyways, just know that it reduces the voltage spike, but yeah, I mean, if you look it up, you'll see it's kind of hard.
Yeah, if you do have questions, we'll let you know. Okay. So here's a little bit more about transistors. So they don't only act as an on or off switch, they also act as variable gates. So depending on the type of signal that I pass into my pin, it could, what's it called, let in different amounts of current, and this essentially allows us to control the motor speed, which I'll talk a lot about later in the later slides, so don't worry about it. But basically, depending on the signal that I give into the pin, we're able to control the speed because it varies the amount of current. Do you guys have any questions? That's
Aside from the
aside
fly
from
back,
this,
yeah.
Okay.
Okay. Alright, let's see. Alright, so now we've established that motor on-off state and our diagram will work. So if we wanted to like make a mouse which could only turn motors on and off, we could do that. But we want to do more than that. We want to be able to control the direction and speed. And so we'll look at direction now. So if we make a system, this is just the same thing, the same circuits we had earlier, except we've connected 4 of them essentially. And so now, instead of just going through one of the circuits, we have, this is our battery up there, by the way, and this is ground. And so we have 4 of them connected, and so we can apply voltage to any 4 of these bases of these transistors. I think there's like animations or something. All right, so does anyone know what happens if we apply voltage to Q1 and Q4?
So diodes can only flow in one direction.
Yeah.
And those are just transistors, but now there's 4 of them. So this is going to be the general schematic of, just general diagram of how we're going to control our motors. So what do you guys think would happen if we were to turn on Q1 and Q4? That means that the transistor for Q3 and Q2 are turned off. So where would like current flow through?
Would it go through Q1, go through the motor, and then go through Q4, and then towards ground?
Yeah,
Yes,
that's exactly
perfect.
what happened. And let's see if it shows. Yeah, the current's gonna go right through the motor, and I'm sure there's some convention, but it doesn't matter. Basically, when the current goes one way through the motor, it's gonna move in some direction. So let's just say it turns clockwise when it goes from the positive to the negative side of the motor. And because of that, we can control that direction. And so now we just have to ask what happens if we turn on Q2 and Q3. And now this time Q1 and Q4 are off. The base has no voltage applied.
What do you guys think would happen now if we turn on? Okay, sure.
It's the other direction.
This is true, yeah.
Yeah.
It's gonna go left of the motor, and effectively, this is gonna make our motor move in the other direction. So this time it's gonna move counterclockwise. Here's a bonus question. What happens if we turn on all 4 of these? Alright, it's like sort of a trick. I mean, basically, don't do it. It will just short because it will not go through the motor. You can see, like, if you just turn on, even if you just turn on Q1 and Q2, the current would just flow to the left and towards ground and not go through the motor because there's no reason for it to.
If it shorted in this scenario, would it kill any components?
I don't know. It might just not do anything, but
I think it would just.
yeah, I think it would just not do anything.
Because like the diodes prevent it from. Yeah. So
The flyback diode, I mean, it's not going through it like in this state where no pins are activated, but like for the same reason when we disable Q1 and Q4, we need those flyback diodes to prevent that back EMF from destroying our.
So if it's enabled, sorry, if Q1 and Q4 are turned on, so it goes to the motor, and then which path does it take to ground?
So,
Isn't it
okay, so
Yeah, I can't go
okay,
through that.
these flyback diodes, like we said in like the previous slides, they only allow current in one direction, right? So, okay, you can think of them as just arrows. So like if it's like this, that means it can only take current up here. Same thing here, here, here. So say Q1 and Q4 turned on, right? So VCC, wait, if you guys don't know, sorry, that stands for our power. So VCC, it's gonna be here. First thing, it's gonna check like, it's gonna go either through this path or this path, but Q3 is turned off, right? So this entire thing just shut off. So now it's gonna go through Q1, and because Q1's on, it's gonna flow all the way down, but it cannot take this diode path because it only allows current to travel from here to here. So it's gonna go through this left transistor, and then Q2 is also off, so it can't flow to the ground. And then again, this diode path restricts current to flow through this path. So then the only other path it can take is through the motor, which is what we want. And once it goes through the motor, it then, Q4 is on, so again, it can't take this diode path, right? Because current can only flow from here to here. So it has to take this transistor, and because it's we call it a closed transistor, but like, it's able to flow through Q4 and then back to ground. So your motor's able to function.
So, why can't it go through D1, like that one?
So,
I think, are you saying like when they're on?
Yeah, when Q1 and Q4 are on.
Because the current travels from high voltage to low voltage, so it has literally no reason to go back up here because it's trying to go to the low voltage ground down here. So yeah, the only path it can take is this way.
oh yeah, that's a good question.
Yeah, I think that might have been what you were asking. Yeah.
Oh, my bad. I'll try.
Yeah, so it just won't go up there. There's no reason for it to go up there.
Like that's the whole point of the flyback diode.
Yeah.
Control the direction.
But this is just to control one motor. Do you guys have any questions?
So just to go over like the Faraday's law, like example here.
Yeah.
So when like if Q1 and Q4 are on initially and it's going through the right, when it gets shut off, the current will still be going through the right. Like the back EMF will still be going through the right. It'll go through like what diodes will it go through if it wants to kill the back?
So, okay, if there is a back EMF, right, it's probably going to be generated like right here, maybe. If it's like this, it's probably going to be generated like right at this point. And since there's a higher potential here, it would just take this diode up to the battery. Yeah.
Okay.
Okay, yeah, again, so essentially we're gonna group these. So like Q1 and Q4 are one grouping, and that specifies one direction, right? Like, yeah, Q1 and Q4 group, that specifies one direction. Let's say it's clockwise, and then if Q2 and Q3 are on, that specifies another direction. So that would be counterclockwise. And again, if you turn on like 3 or 4, it's gonna short, so, or 4, just, yeah, it's gonna short, don't do it. Oh, okay. So now for the actual component that we use for a mouse, the actual integrated circuit that we use, it's called a dual H bridge. And like the name suggests, it's basically 2 H bridges. So that diagram you saw, basically 2 of those to control 2 motors. And this is like the pin layout for it. And again, it controls 2 motors, and that's 4 different inputs. So remember how I said last slide, like we grouped inputs to specify directions, right? like Q1, Q3, that's clockwise, or I mean specify clockwise. Q2 and Q4, that's counterclockwise. So we have 2 of those, and then for 2 motors, so that's a total of 4 inputs. Okay, and then we also have 4 outputs, and that's basically saying if one motor is clockwise or it's counterclockwise, and then if the other motor is clockwise or counterclockwise. So there's 4 different types of outputs. And then dual H bridges also have enable pins. So these enable pins basically turn on or off the H bridge, and it's used for safety and to reduce power consumption. Basically, we don't want voltage going where we don't want it to, so it just prevents like the motors from turning on where we don't want it to, in case like anything like accidental happens.
Oh,
Wait, that's also mine.
okay.
Okay, so this is the schematic that you guys will be designing in your like next assignment. I don't know if you guys started 1A or 1B, but 1B also had like the voltage regulator one. This one's pretty similar. It's okay if you haven't started yet. You guys got time, but you can't really see it that well. Yeah, I know. But okay, this is the dual H bridge schematic. But the main part we want to highlight is this. So this is our decoupling capacitors, and it's connected to VS, which is our main power supply, and VSS stands for like, it's also our power supply, but this controls the logic gates inside the integrated circuit. Don't worry about that. Just know that like VS or anything like that is kind of power. But what these decoupling capacitors do is they basically just remove noise. So like how I mentioned before, there's like some voltage spikes or voltage drops, and these capacitors just kind of smooth it out. So it's good. Okay.
I mean, I don't know what else to say here. Like these are the components that we'll use. Actually, we don't use this, do we?
No, I think that's just another one.
Yeah, these are examples of H bridges. This is the one that we'll use, and so we'll, I mean, I don't know if we'll use it. Someone say something?
You guys have any questions over like how we like specify the direction now for motors?
Which one are you using?
Which
Oh,
one? Oh, okay.
we're using L293D.
That black one. That one looks like
Because you just said this one, but like didn't point at anything.
Oh yeah. This one, right here. You can see it right here. This is this is like the actual board you'll get. Except this is, it says 2021 to 2022 on it, which is not the current year. All right, see yours. Okay. All right. Now we know how to do direction. We know how to turn it on and off. And again, we could literally build a mouse like this. Like it would, I mean, it would be a lot harder to do cool things, but we could do this, and so it would work. But we want to be able to specify the speed of our motors, and you know, how do we do that? Let's find out. All right. I mean, I guess this is a given, but basically, when we enable those pins or whatever, we can basically only control the motors to work at 100% capacity or 0% capacity, and I don't know. That's like not very helpful. It's hard to control something when you can only move as fast as possible. It's like if you try to get around the hallway just by sprinting or standing still or something like that. And so we want to be able to not. We're going to be able to go in a range between 0 and 100% capacity. Thanks.
Yeah. So, like Michael said, like right now we're only able to go 100% speed or 0% speed. So what if we wanted something in between, where that comes in with pulse width modulation or PWM. So instead of turning your motors on for long periods of time or turning your motors off for long periods of time, what pulse width modulation suggests is that you're essentially toggling like the button like hella fast, like thousands of times per second. And what this allows it to do is it first, like when you press it, right, it's gonna make the motors turn, but then right when you stop it, there's gonna be some inertia, and it's gonna continue allowing the motor to turn for a slight bit, and right when it's about to stop, you're turning it on again. So it's still continuing to move regardless. So that's how we kind of like vary the speeds. And some key terminology that we use is duty cycle. So that's percentage of time it's in the on state, you can think of it as like speed. So like 100% duty cycle, that's just on 24/7, and then like 75% duty cycle, like 75% faster, 50% faster, 50% duty cycle, and I mean the math for it is time on over period times 100. And what is, if you guys don't know what a period is, that's basically one of these on and off. So this is a period, this is a period, and then, but yes. So you're essentially toggling it on and off so that you can vary the speed. And you also have frequency, so that's the number of cycles per second. Do you guys have any questions for, okay, that's good.
Alright, so, yeah, I've looked at these. Alright, so we have to ensure that our input pins are going to be compatible with our H-bridge. Basically, all this means is that we need to like calculate, I don't, there's a term, and, oh yeah, we need to calculate like our counter period, that's the term. And it's going to have to do like with like some common multiple of our MCU clock speed and our H-bridge's max frequency. And so, I mean, you could see the simple math here. We just divided the divided the clock speed of the MCU by the frequency of the H-bridge to find this number. I actually don't think that's like, because you could do like multiples of that or something like that, or I could not greater multiples, but less multiples. Like you could do 1600 clock cycles. You could do 800 clock cycles. It shouldn't make like difference, but I mean, if you get really low, you're gonna start sacrificing like how precise you can be. Like if you've got like 2 clock cycles, then you can only either, you can only have 0%, 50%, or 100%. And so that's why just more, we want to use the most clock cycles so we can have the most precision. And our another term is just the pulse value, which is just the amount of clock cycles we're going to stay on per period. So these are like a bunch of buzzwords and stuff, but it's really not that hard. Basically, we have a counter period, 3200, and the duty cycle is just how is the percent that we keep it on, or the percent that of these clock cycles which we have the motor on. And so we have an example right here for a 75% duty cycle, which is basically we just keep the motor on for 2400 cycles. So 2400 over 3200 is 75%. So we're keeping it on for 75% of the time and keeping it off for the other 25%. And then these are like, if you're wondering what these are, they're just visualizations of it. So like the block side there, the wavelength is the same every time, but we control when it's on. That's like what this height phase is, and then we control when it's off. So these are, if you ever seen a sine wave, these are like that, but boxes instead of nice fluid lines.
Wait, also like the MCU clock speed, if you look, it's 16 megahertz, so that's 16 million hertz. And then, but then our H-bridge's maximum frequency is only 5,000 hertz. That means like the MCU clock speed correlates to how fast we turn it off. It controls the pin out. You know how we turn the motors on or off? That's basically saying that the maximum times we can turn it on or off, it's way faster than what the H-bridge can technically read. So what you're getting is like yeah. But okay, it's like, okay, let's say this is the MCU's clock speed. The H-bridges would be like this. It's like extremely slow. So, but the thing is, everything depends on the H-bridge's frequency since it's slower. So, if you were to toggle the MCU's clock speed faster than this frequency, it might not be able to read anything, or just like low-key, like anything could happen. So what the counter period is used to do is basically like suggest that like one of these, everything operates on this, so this is one period, right? So you want to fit 3,200 of these clock cycles into one of these. So a clock cycle is just on or off. So you need 3,200 of these to be put in one of these. If that makes sense, hopefully. Okay.
Yeah, I mean, yeah, and also just know these are not magic numbers. Like 3,200 clock cycles is not like super specific or important or anything. It's just easy and helpful to use that number. Yeah.
So if you're reading at like if the H-bridge is reading at like 5 kilohertz,
Yeah.
and the MC is toggling at like 16 megahertz,
Yeah.
So then it's just like, how is it able to like read the number of like toggles it's getting if the like frequency is like smaller?
It's exactly.
Oh, exactly. It just doesn't.
It just doesn't.
It just
So-
doesn't. Yeah.
Like basically, I mean, a way to imagine, yeah, like we wait 3,200 of the MCU clock cycles, and then we like tell H bridge something or something like that, so that it's in time with its frequency. I mean, that's not exactly how it's going to work, but that's basically it. And so there's so much more time that the MCU could be doing stuff that the H bridge just wouldn't even know. Oh.
Okay. Yeah, but that's
Yeah,
So
that's what I was showing you on the board. But all right, I think. Okay, we did all those parts, but now we need to like do some more stuff.
All right. So now that we talked about how we turn on our motors, how we get like orient the direction of like which way our motors are rotating, and our speed, we just need one more final thing, and that's to track like where we are in the maze. So we're building a maze solving robot, but how do we track like our how far we've traveled, or just the distance covered? So that is. Love that.
I didn't look at these before, by the way, but I know. So encoders basically are going to continually measure the rotation of our motors. This is useful because like we know we can use like how many times our motors have rotated to like quantify where we are or how far we moved or something like that. Also our speed as well, because you can track the number of or how many times it's rotating per second or something like that. These are two examples of encoders. There's a magnetic encoder, which basically uses just magnetic fields to count rotation or fractions of rotations. And then there's optical encoders, which just use light to do the same thing. Actually, these ones look simpler. Basically, just like this is the encoder, this like circle here, and then when you rotate it, the light will shine through, and it will tell you that you moved this far, or you've rotated this much on your wheel or something. We're not going to use optical encoders. We're going to use magnetic encoders, and so, oh wait, this is what our encoder looks like, right here. That's what you'll see on here.
So, like Michael said, we're using magnetic encoders, not optical, and they basically just sense changes in rotational position as the motor spins. So, what are the components for our magnetic encoders? Well, the first thing is we have a 6-pole magnetic disc. So this is a permanent magnet. So it has just like it has 60 degrees between each pole with just north and south alternating. And then we also have 2 Hall effect sensors, and these are the 2 Hall effect sensors right here. And they're basically 90 degrees between each sensor. And together they're put on like the back of this motor, and the 6-pole magnetic disc is actually on the shaft, so it rotates with it, whereas this bigger piece, the 2 Hall effect sensors, they stay stationary. So what you'll see in the next few slides is that this magnetic disc is going to continuously rotate, and these Hall effect sensors will just sense how much it rotates and just like count up the amount of poles that it sees. And it uses like magnetic field.
Yeah, you don't need to know like how the Hall effect works. It's just basically in the presence of a magnetic field, there's voltage differences, and that's what allows us to count. All right. Is it gonna turn? Let's see. Okay. So we say the magnetic poles on the like physical permanent encoder was 60 degrees apart, and the Hall effect sensors are 90 degrees apart. Basically, this means like there will be 30 degrees per encoder count, and actually, let me draw a line. That's like the best way to. That's what I did on like my presentation that I did.
You did?
Yeah. So, what was it? 60 degrees, 30 degrees. So I'm gonna go by multiples of 30. Right. 30, 60, 90, 120, 150. Right? Yeah. Okay. 180.
Yeah, that's right.
And so, let's say, so all of our poles are 60 apart, so this is north, this is south, this is north, then our Hall effect sensors were 90 apart. Let's say we started at this, so sensor, sensor, and sensor. Okay, wait, I didn't have this right. Wait, yeah. All right. It was kind of annoying, the way that is oriented. So basically, this is kind of a bit off to me. Does this look like to scale? Okay. Yeah, it looks good. So basically, if you can see here that at any time, the next time one of these encoders or these sensors will be triggered can only be 30 degrees away. So at this moment, our north sensor is only 30 degrees away from our first Hall effect sensor. So if our motor, let's say this is turning left, what is that? Counterclockwise. If our motor, or if our encoder moved by 30 degrees, it would be over the sensor and it would activate. That makes sense? And so for the same reason, if I need to draw this extra one, 210 sensor. This would be if these are looping essentially because it's a circle. But if you can see for the same reason, if we were to go right or clockwise by 30 degrees, we would reach this sensor right here. Basically, all you need to know is that they're 30 degrees apart, or even though they're 60 degrees apart on the magnet and 90 for the Hall effect sensors, it gives us an accuracy of 30 degrees per encoder count.
So every single time that the magnet rotates, the Hall effect sensors will be sensing one of the poles every 30 degrees. That's the main thing.
All right, and then I think, oh wait, so this was man, this is kind of annoying. Okay, so we're going the CW clockwise. Okay, so we're going clockwise at 0 degrees. You can see that our north pole is detected by our first Hall effect sensor, and nothing is detected by our second Hall effect sensor. If we move 30 more degrees, what will our first sensor detect? Does anyone know? Yes, nothing. And, it writes it there. And then the second one will detect a south pole. And then we can continue this exercise. When we turn 30 more degrees to 60, our first sensor is going to detect the south, and then nothing for our second one. And then continue on. Continue on. Does that make sense to everyone here? Okay. If we do this counterclockwise, we'll get some similar results, but actually you'll notice. Just gonna go through them. I guess I can ask. Does anyone notice anything different between the two, other than that? Yeah. Do you notice anything different? All right, that's all right. Basically, if you see here, you can just notice the patterns here. So first, at least when we started with the north one, when we moved 30 degrees, our sensor 2 detected a south pole. But on our counterclockwise spins, we detected a north one. And so if you see north-north, but that one went north-south, south-north, so this one's north-north, south-south. They're basically different phases, and we can use this to know which direction we're going in. So if we detect this pattern from our encoders, we know we're moving in this counterclockwise orientation, and if we detect that pattern, we're moving in a clockwise orientation. I don't think the encoder doesn't necessarily use that to detect counterclockwise or clockwise, but it uses that to detect positive and negative encoder count. So if you turn 30 degrees, you'll have one encoder count, and then if you turn back, you'll have 0 or something like that. It keeps track of that as a way to know how far you move. Because if you were to move one encoder count forward and one encoder count back, you would have effectively moved nowhere. And so that's why it tracks it like this. Does that make sense? All right. Oh wait. Yeah. Spin direction, we can tell, and phase difference.
Okay, so there's some math. So how precise are our encoders? So like Michael said, we get an encoder count every 30 degrees, and what's it called? One full rotation is 360 degrees. So one full motor rotation, we actually get 12 counts per motor rotation. But the thing is, we also have a 30-to-1 gear ratio, which Michael mentioned. Like, hold on, let me go back to it.
Where you go all the way back?
Wait, no, just like, okay, just this one, bro. Like, so there's like a small shaft here, and then like every single 30 times that one turns, the big one turns one time. And this adds torque and stuff. So that's good. So that's why we have that. So technically we have 360 counts per wheel rotation. And the reason why we need a lot of counts is so that we could, like, it just adds more precision, right? And here's the wheel dimensions which you can use to calculate how many counts you get. So a wheel dimension is 3.2 centimeters, and then diameter 10 centimeters, and then using some math, every single time you get 36 counts per centimeter that you travel.
Which is like pretty precise. I mean, yeah.
So
So it's useful. Although you could get more precise encoders and stuff like that, but for our purposes, we don't need it. All right. We also, I feel like I wanted to say something else. I forgot. Oh yeah, and like, I feel like there was one line not drawn. Oh, yeah, you can.
You
go first.
mentioned like getting more precise encoders. Would you just like increase the number of Hall effect sensors, or would you?
Yeah, you could do that. You could.
That's a
you
good
could
option, yeah.
change the number of poles or something like that.
Yeah.
I'm sure there's many ways to do it. Yeah. Also, changing the gear ratio of your motor would affect that.
yeah, but yeah, that's a good idea.
And so I was just going to connect that line. So basically, when we look at this, so you can barely see it. I mean, here he pointed it out, but like that little like gray thing in that motor is like the motor shaft, because that's how we just put the encoder. We just put it on the motor shaft in the back. That turns 30 times every time that big one moves. So I just want to make that clear that like, so when we say 30 degrees, like it's that motor shaft moving 30 degrees, not the big one in the front. It's not every time your wheel moves 30 degrees. Which is why it gives us a lot more precision than you might initially think. So you might be like, oh wow, 30 degrees. What even is that? 360 divided by 30. Like 12. All right. You know this? I don't know. I can't group this together. Yeah. Yeah, okay, I'll just read this out because I don't know. I'm sure I know what this means, but like for some reason I can't group these together right now and like connection between them. So when I say timers again, we never talked about timers.
Okay. This isn't the like most important to know, but it is what we use for our Micromouse. The counters, they basically just keep track of the rotation, right? And we have two Hall effect sensors, and these correspond to two MCU pins, and as well as two timer channels. And then a special thing is when we do code it, there's a special thing called encoder mode, and this basically just interprets the signal for us. So these Hall effect sensors, they report like, they send signals to the microcontroller, right? But we have no idea like what it's reading in. So this encoder mode basically interprets that signal for us, so we're able to read it as encoder tags.
Thanks for that clutch. That was probably the most important thing in the whole slide.
Yeah.
Yeah, you don't have to like interpret the signals you get from those encoders yourself.
Yeah.
Or the MC will do it for you.
Okay. But just as a recap, so we have our microcontroller unit, right? And it's gonna send a signal on how we wanna control our motors, like the speed, the direction, and if it's on. And it's gonna communicate that to the H-bridge motor driver. And from the H-bridge motor driver, it'll then communicate how it wants the motor to turn to the motor. And as the motor rotates, the encoders will basically record how much it rotates and keep track of that position and or like record data for it and send a signal to that back to the microcontroller, where we then have the microcontroller encoder mode decode that information for us so that we can read it as like encoder counts. Do you guys have any questions for what we just went over? Anything at all? Timers numbers are a bit tricky. Yeah.
This is like the flow.
Yeah.
I still don't get the, maybe I'm because I keep like, I don't get the diode part.
The diode part. Okay.
Yeah. We don't get it either, apparently.
Wait, are you talking about the flyback diode?
Yeah, we're like, we'll talk about the H bridge.
Yeah.
Why? What was the purpose of the diode serving? The current of the flow?
So the purpose of the diode is kind of like the example that we showed. But it's kind of like the purpose that we showed in the previous one, where it's like, do you remember this one? Where we did this? Wait, so you were okay. But when you do turn off the motor, there's going to be a change in current. There's going to be a decrease in current, and this causes a decrease in magnetic field, which then causes also a decrease in magnetic flux. And this creates an induced voltage at this right here, right? And this induced voltage acts in a direction that wants to continue the current flow. So it's gonna want to go down here to ground. But the thing is, this path is cut off. So the only way that current can travel back up is through the motor and through other components back to the battery. But that isn't what we want, because it could damage sensitive components. So the flyback diode acts as a way for it to avoid other components and go back to the battery. Yeah. Oh, okay, so the mechanism that's cutting it off is a transistor. So this is how we essentially turn on or off our motor. So a transistor just acts like a switch that connects the battery to the ground, and then it resends voltage to the pin it'll connect.
I can draw it right here.
Does that make that first one? Yeah, which is honestly why I didn't join it. I feel like
Wait, so
if it does something,
We're gonna go over
yeah, right? Like no matter what you do, like research wise, like you I mean anything and everything at the end is what's up. Yeah, that's a thing. So I think you should do like I guess it. I think Micromouse is still useful though because you learn fundamentals. Like it's not really like sort of the robot may not apply to what you're doing, but like the fundamentals you learn are like really Gotcha. Yeah. Well, that's
But the PCB design is like it's something you'll use universally.
yeah.
Right? It's like yeah. Well, it's nice meeting you, bro.
Let's go. See you Friday.
See you Friday.
Wait, they have the reserve, the root reserve.
What's it called? So, okay, you filled out the form. Okay, you might just be still after. We'll update you as soon as it's done. Thank you. Wait, sorry, what's your name? That's what I Jane?
Me, but don't.
We changed it up like a lot.
Like,
So.
you're about to give
But the
me
games are
money,
Sundays,
but
like,
write
I
down
do-
your
I do
name
like-
paper and then give it to me with the money so I can. Okay. Message me
Or
on
wait,
Discord.
you could usually come back anytime in the
No,
lab.
just give me the money right now. And then just message me on Discord. Yeah, message me on Discord right now and just say, my name is this. I gave you $50.
We just had it today. Usually we don't. Hey, sorry, what's your name? Okay. Yeah.
But yes, but he messaged me on Discord right now. Be like, this is my name.
Okay.
I'm paying you in cash.
Yeah, that's a bit tough this week. We're at like we accepted a lot of people this year, so it's pretty tight. Wait, if you want, just message us on Discord. But we can try. But right now, like,
For what?
he just like learned about entrepreneur like recently.
Yeah, I'll let you know. Because some people left.
Yeah.
Okay.
But like, message me and say like some shit. Like, send me. No, just do it right now. Like, while Actually, wait.
I actually had a friend who added me to Discord. So
Okay. Wait, leave the room first because of this club. But
okay.
Sorry, you guys have any questions about the
Let's leave the room.